Hi, welcome back to Missing Chemistry. This is electron configuration of Tellurium, TE. Well, Tellurium happens to be element number 52 on the periodic table, so let's go and write that. There you go. And its AMU happens to be 128. Pretty darn cool. That's what I have to say about that. 52 protons matches the atomic number, and 52 electrons make it electrically neutral. What about the number of neutrons? Really love those neutrons, huh? They have no charge. So you have AMU minus protons equals the number of neutrons. Oh, so we go 128 minus 52 equals 76 neutrons. Pretty darn cool, I would say. All right, so let's go ahead and let's get rid of some of this excess light here. Clear the board up a little bit, make it a little bit nicer. All right, now when we get into electron configuration, it's important to remember that the S subshell holds 2 electrons, the P subshell holds 6 electrons, the D subshell holds 10 electrons, and yes, the F subshell holds 14 electrons. We're going to fill by the off-ball principle, which says you fill the lower shells first before you fill the upper shells, right? Right. So we use the diagonal rule, and that's these red arrows right here. And we just go down these slides until we run out of electrons. In this case, that would be 52 electrons we got to get. All right, let's do this. 1s2, oh yeah. 2s2, oh my, look at this, how easy this is. 2p6 and 3s2, 2p6 and 3s2, right? 3p6 and 4s2, 3p6 and 4s2. Wow, that's cool. 3d10, 4p6, 5s2, 3d10, 4p6, and 5s2. Pretty darn snarly is what I have to say. 4d10 and then 5p4. 4d10. 5p4. Just amazing. That's what I see. Well, now let's go to our orbital notation. Now we're going to use Hund's rule. Remember that Hund's rule basically states, more or less, that in every suborbit, you have to put an up arrow for every suborbit you have in that particular orbit. Then you start the down arrow, more or less, right? So like 1s, up and down, 2s, up and down, 2px, 2py, 2pz. Now watch this. Every suborbit's got an up arrow. Now we're going to have the down. Pretty easy. I mean, really, think about it. Here comes our 3's. 3 going up, and then 3 going down. Pretty darn snarly, I say. That is just so amazing. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right. 4px, 4py, down. 5s, up and down. Then look at 40x squared minus y squared, 40xy, 40yz, 40xz, z, 40z squared. Okay. So we're going to go 4, 5, 6, 7, 8, 9, and 10. And then we have 4 electrons left. 5px, 5py, 5pz. Up arrow, up arrow, up arrow. Now we start down arrows. There you go. Look how easy that was. And it was easy. Now, you'd think that xenon would be Tellurium's noble gas notation, but it's not. It comes after it. You can't use the ones that come after you. You can use the one that came before you. The next one that came before them is krypton. All right, so let's go ahead and do a valence shell there. There's our valence shell. So now we're going to write it numerically in order down here. 4d10, phi S2, phi P4. All right, what about our quantum notation? That deals with Pauli exclusionary principle that clearly states that no two elements can have the same set of quantum numbers. And I totally agree with that. So think about this. Tellurium is in the P block and it's way over here, right? So the principal quantum number, of course, of this is going to be 5 because it is in the fifth energy. Okay, the L value is going to be 1 because it's in the P block. The M value, so you go -1, 0, 1, repeat, -1. So it'd be -1 in this case. And then our last arrow, which is right here actually, is going down, right? So that's going to tell me a couple important things. It's going to tell me that it's 1. Just amazing stuff, guys. We'll see you back here, and you be snarly at Moosing Chemistry.